All right, so let's talk about hydrides. And specifically, let's talk about hydrides, which of course are just H- nucleophiles, way to add hydrogen. So there's two main types that we've seen. There's sodium borohydride, and there's lithium aluminum hydride, or LAH. And the difference is major difference in these two is reactivity. The sodium borohydride is just less reactive. Right? It's less reactive. So it's a less reactive nucleophile, and this is obviously then more reactive. And as we start to think about nucleophiles, electrophiles, it's going to be important to kind of match them up. Right? If we have a less reactive nucleophile, right? If we have a less reactive nucleophile, what kind of electrophile will we need to have to make it react, to have something to react with? We actually need a more reactive electrophile. And we'll get to that in a second. So first question is, why is sodium borohydride less reactive? Well, it's a periodic trend. So hydrogens are all staying the same size. They're not changing their size in all these cases. So the difference must be between the aluminum and the boron. So the aluminum is actually lower on the periodic table than boron. So it's bigger. Boron is higher up, so it's a little bit smaller. Now that size matters because when we think about bonding, we think about sharing electrons. If two atoms are similar in size, they're going to be able to share electrons much better. Their orbitals are going to be able to overlap better. It's going to make a less reactive or a stronger bond. Whereas a larger atom, right, because it's just bigger, it can't share the percentage of electron density as much as a smaller atom. They don't match up well. That's going to make those bonds weaker, or I would say more reactive. So because aluminum is bigger, these H- are much more reactive than the borohydride, which is nice to know. Now, another thing to take into account when we think about these hydrides, there's a minus charge on the aluminum and on the boron, but in reality, all the electron density is actually on the hydrogens, right? This is one of those cases where Lewis dot structure is not giving us the full picture. It's just balancing the charges. So these are all hydride sources. And the best way, I usually let people just write it as H-. Don't worry about drawing anything fancy. Just draw it as H-. But you do need to recognize that, of course, that lithium aluminum hydride is more reactive than less reactive nucleophile. Okay. So let's take a look now at a little bit, something I call Mount Carbonyl. Mount Carbonyl is just a silly way of talking about how good of electrophiles all these carbons of these carbonyls are. And the way I have them ranked right now is that the aldehyde is the most reactive. Right? So this is like the top of our mountain. Right? The things at the highest part of the mountain are the most reactive. And they're willing to go downhill. So the carbon of the aldehyde is most reactive, followed by the ketone, followed by the ester, the amide, and the carboxylic acid is kind of weird because, right, it's still an acid first. So we always got to think about that a little bit, like what's going on there. But nonetheless, it's not that reactive. So really, if you're looking at these four, and really just carbons of the carbonyl groups, right? Carbonyl is just a C double bond O, C double bond O, C double bond O, C double bond O. The things off of it are what makes them different. An aldehyde, a hydrogen, right, can't do any hyperconjugation, right? Can't push electron density towards that. So this is more reactive than a ketone, which has more hyperconjugation possibilities, which makes this less reactive. What can an ester do that a ketone can't or an aldehyde can't? An ester, of course, can do resonance, right? So that makes it a little bit less reactive. And then an amide, of course, can also do resonance, but it's lower in reactivity because a nitrogen is more willing to do resonance than an oxygen. So that makes this even less reactive because this is doing resonance. So that's why amides are lower than esters as far as reactivity goes. So now you got to think about matching these up. So these more reactive electrophiles, these carbons and the carbonyls, aldehydes and ketones, will match up with a less reactive nucleophile because they're more reactive. They'll match up with a less reactive nucleophile. And that works really well. Because sometimes you don't want, the big guns, the really reactive things to react with something else that's pretty reactive. Sometimes it's nice to use a more mild reagent to react with something else that's reactive. So a less reactive nucleophile with more reactive electrophiles. Now, lithium aluminum hydride, because it's more reactive, it can go to work on these three. But it also, of course, reacts with these if they want it to. So lithium aluminum hydride, because it's so reactive, it can react with all of these, no matter where they lie on the mountain. Even if they're down here at the bottom and really unreactive, with not very reactive electrophiles, with lithium aluminum hydride, because it's such a reactive nucleophile, it'll still react. Right? So thinking about matching nucleophile reactivity with electrophile reactivity and understanding those concepts.